Let's look at, what do you mean tomorrow's the bad day? I'm very optimistic about this test because I've already given you a third of it, right? You just have to practice those 4 questions, and some of those are pretty easy. The first one's kind of hard, but the other 3 are, if you get the first one, if you know how to do it, it's easy. It's all easy if you know how to do it, but I'm very optimistic about it. I think that we're going to have the highest average I've ever had before. There are 20 multiple choice, and one of those is, the version. Sorry you don't get a snarky, who's my favorite student question, or whatever. Sorry. Hope that's okay. All right. Somebody asked about question 4 from the OpenStax. I want to work it. Somebody asked me over email. Let's see. So the action potential, y'all know this, about the action potential in a cell membrane, the action and the resting potential. Y'all study that in biology? Yes? Okay, good. But the point is here that we have a, 100 millivolts, 100 millivolt potential difference. Delta V is equal to 100 millivolts. I get that from the minus 70 right here to the 30. So there's 100 millivolts from the resting up to the action potential. And I'm told that the cell membranes are 5 nanometers across. So delta X is 5 times 10 to the minus 9 meters. That's 5 nanometers. And I want to know the electric field across the membrane at the time of the action potential. So what is the electric field equal to at the time of the action potential? Oh, hold on. Actually, what we want to do here is use our 30 millivolts. Because it doesn't matter that the difference is 100 millivolts. Really, you want to use the 30 millivolts, which is the voltage at the time of the action potential. So I'm going to cross this out and put 30 millivolts. I think that's right. Let me double check that works right. Oh yeah, that is right. And if you remember our electric field, the units of the electric field are in volts per meter. So if I need to know the electric field across this distance of 5 nanometers, when I'm told that there's a potential difference of 30 millivolts across this 5 nanometers, I just divide the two, because that matches my units. That's sort of what I'm going on there. But as my potential difference across this 5 nanometers increases, then I get more and more electric field. So my electric field is equal to V over X. That's going to be 30 millivolts. That's 0.03 volts divided by 5 nanometers. And that should be 6 million. Let's just double check. Yeah, 6 times 10 to the 6. And that's in newtons per coulomb, or as I like to do it, in volts per meter. Just knowing the units for that will help you to remember that the electric field is just the voltage divided by the distance. This problem was a little more complicated because they give you the resting potential, but the resting potential is not really important. Really what you're looking at is I have a cell membrane, and the difference between this point and this point is 30 millivolts. That's our action potential that causes the propagation of this electrical signal along the axon of your neuron. Okay? Yeah, Seth? Why are we converting the top part? The 0.03, you mean? Because it's given in millivolts here. Right here it's given in millivolts, and that's not your SI unit. You want to have it in volts. All right? There's not a lot of unit conversion on the test, but you might have to do some. I don't even know if there's any. There might not be any unit conversion. But can't go wrong with SI units, right? Y'all want to, hey guys, y'all want to look at any of these stand out to you from the OpenStax assignment? Okay, well, let's do number 3 and then we'll do number 12. Oh, look, number 3 is like one of your free response questions. So let's just take a quick look at it. Remember, I told y'all about this. So this is number 3 on the OpenStax assignment. I have a proton at rest in a location where the potential is 5 volts and then it moves to a potential of 3 volts. So the delta V here is 3 minus 5, which is equal to negative 2 volts. Turns out that the negative is not important because I'm just looking for the magnitude of the speed. And then I want to know what is the speed of the proton at that new location. Q times delta V, that's the work that's being done on that charge by the electric field that is the result of this difference in potential, is equal to 1/2 mv squared. And now I'm going to put in, I'll just solve here for V, that's 2Q delta V divided by M square root. If you want, you can put in numbers for Q, delta V, and M, and then do it that way. But doing it with the variables, it'll help prevent mistakes along the way, because many of your mistakes are made in the calculator. Do whatever you want to do, I don't care. I mean, I do care, but I know that you're not really going to change what you do. All right, so that's 2. The charge of a proton is 1.6 times 10 to the minus 19 coulombs. Delta V is 2 volts. And I'm just sort of losing that negative because I'm only looking for the magnitude of the speed anyway. And then the mass of a proton on your equation sheet has a value of 1.67 times 10 to the minus, what's this proton? 27 kilograms. And that's equal to 20,000 meters per second. Again, this number is the charge of a proton. On your equation sheet, it's the fundamental unit of charge. This number is on your equation sheet. It's labeled as M sub P, an M with a P subscript. You do have a couple of questions, at least, where you have to know those values. Or you don't have to know them, you just have to know to use them. Look for proton, look for electron. What was the other one? 12. 12? Okay, that's a good one. They're all good ones. In fact, I think there are probably 5 or 6 that are explicitly OpenStax tutor questions, but then there are others that are just a lot like them. So know how to do all the tutor questions. Number 12, the hard part about this one is just knowing how to draw the thing. And so I have one charge at x equals 3 centimeters. 1, 2, 3. That's 25 nanocoulombs. And then the other is at y equal 5 centimeters. Right there. So that's 15 nanocoulombs. They're both positive. And then I want to know what is the electric potential right here. What is V equal to? That's the hard part there, is just drawing the figure. Because we've done this problem, and in fact this problem, again, in the free response, I'll give you a collection of 2 charges, and you have to be able to calculate the potential. So for that reason, let's go ahead and work through it, okay? V is going to be equal to V1 plus V2. I'll call this charge Q1. Oh no, let's call it Q2 because that'll follow the problem. And this is Q1. V1 is going to equal to 9 times 10 to the 9th times 25 times 10 to the minus 9. And then I want to know the distance between that point and that charge. That is going to be 5 centimeters, or 0.05 meters. Let's just KQ over R, right? And then plus 9 times 15 divided by this distance, just 0.03 meters. Oh, not squared. And then that's equal to 9,000 volts. Notice here, I did this yesterday in class. I left off the 10 to the 9th because I knew that there was a 10 to the minus 9th just following by. And you'll find that that's true for your exam, that you'll have a lot of nanocoulombs when you do an electric field and electric potential, just because it makes the numbers cancel out. You can just do the numbers on your sheet without using your calculator. You have to use your calculator some, so don't think that just because you're using your calculator you're doing it wrong, but on many of the problems you don't have to do it. And you can not use your calculator and still be doing it wrong, honestly, because I just made the numbers really easy to work with. Okay? Yeah.
For the last question on here, for 13, I got it right, but I'm going to be honest, I lucked out because I guessed, because I had no idea how to do that.
Okay, nothing wrong with guessing. Let's see, electron accelerates. Okay, so you want to know, let's see, give the distance. Oh, so this is like the one that we were working before, right? That I know that the work done on a charge is equal to Q delta V. And that causes an increase in our kinetic energy because you know the work energy theorem. And so I say Q delta V is equal to 1/2 mv squared. And then I need to go through and pick out all the numbers. Now I'm looking for, what am I looking for? Delta V. So delta V is equal to mv squared over 2Q. And so now I can pick it's an electron, so that's 9.11 times 10 to the minus 31 kilograms. V is 10 times 10 to the fourth, that's 10 to the fifth meters per second. That's just the 10 times 10 to the fourth. I just wrote it a little more simply. Divided by 2, that's from the 1/2, and then Q is 1.6 times 10 to the minus 19 coulombs. And then that'll give me the 0.029 volts. Must know how to do those. In fact, even though it's on the free response, doesn't mean that you won't see it in the multiple choice too. Although the multiple choice problems, I know that you have a Coulomb's law problem in the multiple choice. We have to calculate it. I'm pretty sure you have one like this that's similar but different from the free response. There are only a handful of calculation problems. Most of the multiple choice are, what's the word, conceptual. Doesn't mean they're easy. Oh, you're joking, okay. In fact, I found, like in my 201 class, which our exams were like 10 multiple choice, and then the rest were free response, 5 to 7 free response. So they spend most of their time on the free response questions. That the students preferred the free response because they found that they scored better, and sometimes they did. That the multiple choice, they didn't like it at all. You don't like the multiple choice either? I know. I understand. You can always ask me if you're just confused about the language. You can ask me, and I might not say anything. That sometimes students will call me over and they'll ask me a question, and I'll just sort of repeat back what they said to me. But if it's something that I can clarify, I absolutely will. All right, what else? Any other on these? Number 7. Okay, this one is similar but different. So similar to this, it's talking about work. But remember that work is force times displacement, right? And then when I'm talking about an electric field, that force is Q times the electric field times displacement. I think on your equation sheet that this is QE delta X, that the work. Isn't that right? It's on your equation sheet, I'm pretty sure. So my work is QE times the distance. And so that's what I'm looking for here, is I'm looking for the work. So now that I know the equation I'm using, I have everything that's given. Q is for an electron, so that's 1.6 times 10 to the minus 19 coulombs. E is 50 newtons per coulomb. And then D it's going from 0 to 20 centimeters, so that's 0.2 meters. And then that's going to be 50 times 0.2 is 10, so it's 1.6 times 10 to the minus 18 joules. Our Newton meters is the unit is for work. All these are great questions, okay? So I want y'all to be prepared. The tutor assignment is a great place to practice for the exam. Okay. What else?
Okay, so I think what's confusing me is the electric field with the lines. You have a rule that says the lines are equal to the magnitude.
Right.
Like you would think 3 coming off equals a 3 charge.
Oh, but that's not what I mean.
That's what I keep thinking.
Yeah, because it means that if I have a 3 coulomb charge, so I have 2 charges, and I have field lines going here. Now let's say, I don't know, this is 12 coulombs. I have 5 lines and 12 coulombs. Like that, that's sort of odd. It seems like I should have 12 lines or 6 lines, something even. But the way you approach these is, first of all, now I would ask you, what is this charge on the right? First of all, determine, is it positive or negative? And it's going to be negative, right? Because the field lines are going into the charge. And then and then you might be able to go through and say, well, it's not this, this, or this. And then you could also ask, well, is that charge bigger or smaller than 12? And in this, it's got to be something smaller than 12. That might be all that you have to do, and then you're done. But if not, if there's still some options, then you can say, well, each of these lines right here is worth or equivalent to 12 divided by 5. And so 12 divided by 5 is 2.4. So each of them is worth like 2.4 coulombs. They're not worth anything, right? They're just like a map. It's like drawing a topographical map. You can put as many lines on a topographical map as you want, but the lines are going to sort of change the meaning the more lines that you have. But in this case, each line is worth 2.4. That means that this charge is going to have a value, because it has 3 lines, it's going to be 3 times 2.4, or 7.2 coulombs, negative 7.2. So you want to figure out how much each line is worth. You can set up a ratio too. You could say 12 is to 5. As Q is to 3. And that would work as well. 36 divided by 5. Yeah. That might be an easier way. It depends sort of the kind of person that you are. What kind of person are you? The first one? Yeah, I think that's probably a little more intuitive. But you think about, what are the lines worth? But if you're a ratio kind of person, do the ratio. Are you a ratio person? Do whatever you want. We've already determined that. I don't care, right? As long as it's right. Do it right. Okay? What else? Sure. So with the capacitors, you'll have one question that I'll ask you: what is the capacitance of this? No trickery. It's going to be a problem, a word problem. I'll give you the kappa, I'll give you the area, I'll give you the separation of the plates, and you know what epsilon naught is. Or you might not know it, but it's on your equation sheet. And then you'll just have to calculate what is the capacitance. You just plug it in. I hope it's a gimme for everybody. So C is equal to kappa epsilon naught A over D. Okay? Do you want me to? I can find one with numbers.
I was wondering if we would solve for anything different, like how would you arrange that?
Oh no, not right now. We might have that on in the next test. But right now, I just want you to understand that capacitance. This is how we find our capacitance, and that it's dependent upon these different variables. But then you'll also have a couple of questions that are more conceptual, like what do I do? What happens if I change the area of the plates? Or what happens if I change the separation between the plates? We did several of those in class. Right, so if I change the area of the plates, if I double this, that doubles this. Or if I have this, that doubles the capacitance as well. I want you to understand the role of dielectrics. The dielectric is given by this, that it increases the capacitance of the capacitor. And it also serves that practical role, that it keeps the plates from touching. And then also, we worked through those problems in class where we said, okay, what if we hook up a capacitor to a battery, like this, and then we change the area of the plates, or we change the separation of the plates. And that's looking at two different equations, Q equals CV, and C equals epsilon naught A over D, or kappa epsilon naught. And remember we had two flavors of this question, and you'll see one of them, I'm not sure which one, but two flavors where if I leave it hooked up to the battery, that means that Q remains, not Q, if I leave it hooked up to the battery, that means that V remains constant. And then for example, if I double the area, that doubles the capacitance. If I double the capacitance, that doubles the charge. So that's one type of question. The other type of question is where I take away the battery. Like I charge up the capacitor, and then I take away the battery, and then I ask a similar question. What happens if I double the area? Well, that doubles the capacitance. But if I take away the battery, it's no longer the voltage that's constant. What's constant on this charged capacitor now? The charge, right? So this is now constant. And if I double the capacitance, I have the voltage. Those are on the concept test. We work some in class too. But as we're going through old tests, if I see one, I will see one, we can work through it. Those are the types of capacitor problems that you shall have. And you shall do well on them. Right? Yeah. You will. Okay? What else here? From OpenStax tutor, don't forget the other one too, you know. Let's look at that other one. These are sort of basic things about charging objects, polarization, charging by conduction and induction. You're going to have a handful of questions, 3 or 4, that are about sort of the basics of charge. Any of these stand out to y'all that you were confused about? Yeah, chapter 2 is harder. Although the field stuff, the people get confused about the fields. Okay? You want to just browse some of our old tests, or do you have particular questions? I figure some of you probably have questions about the old tests. I feel pretty comfortable about it. Yeah. What can I do? You want to look at some old tests? Oh, okay. Good. Is this the one? The one on the right? Okay. Yeah. Well, where is the potential equal to 0? To find where the potential is equal to 0 due to a multiple set of charges like this, you want to find the place where all the positive and negative charges of equal magnitude are the same distance from that point. So for example, this one, the answer is E, isn't it? Okay. Let's switch these up just a little bit. Here the answer is E because like this distance is the same as that distance. That distance is the same as that distance. So when I add up the potentials, they cancel out. Because the potential due to this charge is exactly equal but opposite due to the potential of this charge at this point. But if I switched up the order a little bit, which you can do, if I switch up the order and let's say that I make this -1 and this -2 instead of the way that it is, what would be the answer then? It's not all of them. It's going to be B. Look, if I try to do it at A, right here, the distance there is smaller than the distance there. And so the net potential due to those two charges is going to be positive. Because the +2 is going to contribute more potential. But at point B, they're now the same distance from one another. And so the net potential is going to be 0. That's what you want to look for. The pairs of equal but opposite charges that are equidistant from the point. And if that's the case, then that's where your potential will be 0. All right? But there's one, like you'll see, number 17, just calculating the capacitance. Make sure you know your basic definitions of potential and fields. Yeah, Justin?
Can you do 17?
Sure. So, this one was a little more complicated. I have to first find the capacitance. Kappa epsilon naught A over D. Kappa is 3.7. That's given right there. A is 0.0, or let's do it, epsilon naught. 8.85 times 10, I think it's minus 12. A is 0.04 times 0.05. That's the area of this plate. And then they're separated by 1 times 10 to the minus 3 meters. That's given right there. This is the area, or that's the dimensions. I actually give you the area. I just want to make sure that you know how to calculate the capacitance. Then you calculate that capacitance. I don't know what that is, but if I do that, you know what it is?
I don't remember anything.
Okay. So if I use that, whatever that capacitance is, times the voltage, which is 1.5 volts, then I'll get 9.8 times 10 to the minus 11. Okay? Y'all good with that, right? Yes, sir. They're going to be on everybody's equation sheet except for yours. Like, I'm going to take white out. No, I'm joking. I'm joking. Yeah. It's the same equation sheet as what's on the website, so you'll have all that. Make sure you're familiar with it, okay? That you know what's on the equation sheet. Because sometimes they're sort of jumbled up, and they might even be written a little bit differently. Like it might be, I don't know if that's true, but it could be like V is Q over C or something like that.
What's the difference between the one with kappa and the one without?
Nothing. It's just one has kappa and one doesn't.
That kind of confused me because on my equation sheet they have both of
All right. I'm sorry. Yeah. I think because, I don't know why. I don't know. It shouldn't really be that way. We should just take that off.
The one's like all the way to the bottom and the one's all the way.
Yeah, I understand.
So you just always use the kappa?
Well, if it doesn't have a kappa, the dielectric constant for air or for a vacuum is just equal to 1. So if you don't have a dielectric, then the dielectric constant is 1. All right?
18?
Sure. So what happens if you insert a dielectric material between two charged parallel conducting plates? Okay, so this thing it's been charged and then it's disconnected from the battery. That means that in this equation, Q equals CV, that this is my constant value. Like on these questions, which you'll face one that's, same idea as this, that's what you want to ask. Is my voltage constant or is my charge constant? If I have a battery hooked up to it, my voltage is constant. If I've charged it and then I take the battery away, then I just have a bowl of charge sitting there and I can't add or take away any charges. And that's the case here. So if I add a dielectric, that means that C will increase, which means that V will decrease. So it's not going to increase the charge because there's no battery. It's not going to increase the voltage. It will increase the capacitance. It will not decrease the capacitance. So it's like 3 only. Or I could also say that it will decrease the voltage on the capacitor. Like that would also be an all right answer. Okay? You'll see a question similar to that where you have to ask that question first, which is constant, the charge or voltage, and then what happens if you change that capacitor. It makes a nice way actually to give you a variable voltage supply that I can change the dimensions of my capacitor to change the voltage.
So if a battery is hooked up, the voltage is constant?
Right, if the battery is hooked up, the voltage is constant, and then if you change the capacitance, that changes the charge. Like if you give it more capacity to store charge, then the battery will put more charge onto it. But if you don't have a battery, you can't add more charge. It's sitting out there all by itself, all alone. All right. Equal potential lines, potential of a configuration of charges, that's in the free response. Potential energy type things. Let's see, magnitude of electric field. Your free response will be something like this. A little harder, but this one's kind of easy. That's not easy, but my vectors are like that, so I don't have any off axis. You'll have the added step of finding the x and y components of one of those vectors. This is like what we've been doing, like finding the velocity after it moves through an electric field. We did one of these before. That's like the QE delta x is equal to 1/2 mv squared. Our work is equal to our change in kinetic energy. This is like one we just did where I disconnect it from the battery. Q is CV. If I disconnect it from the battery, that means this is constant. If I double the area of the plates, I double the capacitance, so I have the voltage. Any other particular questions? You know your electric field, force per charge, electric potential, energy per charge, right? Know those basic definitions. Know your field lines, how to interpret your field lines. You can set up a ratio, or you can say each field line is worth the charge by the number of field lines, divided by the number of field lines. Know sort of your basic stuff about you know, charges and how they interact. All right. What else, folks? We have time. I have time. More questions. Are y'all super prepared or not prepared enough? Can't tell. It's gonna be good. I'm excited about it. I'm really glad. That's the way I want you to feel. That you feel confident going into the test. But make sure that you know those first four, because you know as well as I do that the mood of a test is set by the first question. And the first question is the hardest question. But, you know, with practice, you can do it. You know what it is. Right? Those two charges, what's the electric field? So make sure that you know that inside and out, so that you go into it with a boost of confidence. And nailed that 8 points, or 6 points, or whatever it is. Okay? All right. Well, is that all? All right, make sure I get your names before I leave, before you leave. That we